This is a very nice proof of showing how ds dt is going to be equal to dy and dx dt and how they're related, because as point prime moves down the curve, ds is changing, dy is changing, and dx is changing. So as this moves down the curve, what relationship does s, y, and x have? Well, the first assumption we have to use is that the limit as p prime moves to p is going to be equal to 1. So as p prime and the p prime curve, so you have p prime the straight line, p prime the curve. So as p prime moves to p in the curve divided by p prime moves to p in the straight line, we're going to assume that's equal to 1. And the same with the limit as p prime goes to p, as p prime goes to p. Same with delta s, because that's basically this curve is going to be divided by the p to p prime, and that's also going to be equal to 1. These are both the same thing. Basically, what we're saying is that delta s is going to equal to sometime delta s is going to be equal to p prime. If you can zoom in on this curve close enough, Newton says that by all practical purposes, delta S and delta P are going to be the same thing. Is that true? I don't know if it's true. Maybe it's one of those things that Gödel says that in all math, some sort of an equation or some sort of assumption is usually based on something that can't be proven. That's possible, because I don't know if delta S is ever going to be equal to P prime, P to P prime. I don't know. Is 0.9 forever equal to 1 forever? I don't know. I'm not going to answer that. I'm not a mathematician. Or this is more of a physics problem anyway. I'm going to be dealing more with physics than I am math. So anyway, let's look at if this is true, then we can use Pythagorean theorem. If we can use Pythagorean theorem, we can say from p prime to p squared is going to be equal to delta x squared plus y squared. So if we do use this in terms of calculus, ds squared is equal to dx squared plus dy squared. All right, so let's take the limit as p prime goes to p. I'm sorry, p prime to p as delta x goes to 0. So if we take this limit of this thing right here, we take the limit of this thing, we're going to find out that as x goes to 0, this is going to be equal to 1. And this is basically be our dy dx. So since p to p prime is delta s, we have delta x divided by, ds dx squared is going to be equal to 1, because this thing is equal to 1, plus our dy dx squared. This is a really important little proof. It's an important little problem, equation, because we can use it in problems. We can use this thing in problems, and it does have some power to it. But the best thing that we can get from this is if we take the time derivative of this thing. So if we take the time derivative of this thing, we end up with ds is equal to dx squared plus dy. Take the time derivative, and this is a beautiful equation. This equation we're going to be using a lot in physics. We can use it a lot in physics. It can be used to find velocities and accelerations on a continuous curve, as well as position. Position's a little bit harder to find because you're going to end up taking integrals. Sometimes the integrals are a little bit more difficult than the derivatives. But on the next video, I'll show you how we use this particular equation, and it is powerful.